All right, Year 11s. I know a few of you missed last Wednesday's class, courtesy of exams and other bits and bobs. So just a very quick summary to give you a couple of examples of the last little bits of gases. Everything I talk about today will relate to page 12 through to 14 in the gases book. Essentially, just the last little bit. What I would say is make sure that you complete the gases assignment that Ms. Clift emailed to you at the end of last week, and make sure you work through the textbook questions. They will prepare you for what you'll see relative to gases on the exam. And if you've got any queries about the last little bit, hopefully this will help. So firstly, to the general gas equation, very, very useful equation, this one here, but to get it right, you have to make sure that your units are correct, okay? Every other equation that we've looked at, Boyle's law, Charles' law, P1 V1 equals P2 V2, V1 on T1 equals V2 on T2. All of that can be derived from this equation, as we talked about in class. But if you're going to use PV equals nRT, you must remember P is equal to pressure, obviously, but it must be expressed in kilopascals. All right. If it's expressed in atmospheres or millimeters of mercury or pascals itself, this equation doesn't work, okay? Has to be expressed in kilopascals. So just for reference, 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 101.325 kilopascals, okay? So if you get given a question where you have atmospheres or millimeters of mercury as the pressure unit, if you're going to use PV equals nRT, you must convert it into kilopascals using those conversions. Okay. V is equal to volume. Your volume has to be in liters for this equation. Obviously, amount will be in mole, as it always is. Our gas constant is 8.31 joules per Kelvin per mole. And temperature has to be in Kelvin. If it's not in Kelvin, again, this equation will not work. Okay, so remember 273 Kelvin is equal to 0 degrees Celsius. So if you're converting from Celsius to Kelvin, all you do is add the number of Celsius you have to 273. Okay, simple conversion. So let's practice using the general gas equation with this question here. Easiest thing to do if you think you're going to need to use this equation, just jot your 5 pieces of information on the left-hand side. We know that the gas constant will be 8.31. All right. So here we have 0.234 mole. We have 2.7 liters, and we have 24 degrees Celsius. Okay. So that leaves us with pressure as our unknown. Volume is in SI units, we're fine with that. Mole is fine for N, and obviously R is a constant, but we have to convert 24 degrees Celsius into Kelvin. So that's 24 plus 273. So that gives us 297 Kelvin. Okay. So we have our PV equals nRT here. Rearrange it so that our unknown is all on its own. So pressure will be equal to nRT over V. Now we can sub all of these values into the equation. So we have 0.234 mole times 8.31 multiplied by 297 Kelvin, all divided by 2.7 liters. Short calculation later, we get 213.90 kilopascals for our pressure. Now, if we have a look back at our data, obviously here we only have 2 sig figs, here we only have 2 sig figs. We have 3/3 for mole, but because we've only got 2 here, we would want to express this in 2 significant figures. Best way to do that in this case would be 2.1 by 10 to the 2 kilopascals. Okay, and there's our answer for our pressure. You can go back to page 12 of your booklet to try another sample question with PV equals nRT, and also you can complete some of the questions on the gases assignment as well as the text questions. The last little bit of this will be just looking at some stoichiometry that involves gases. So the good news here is there really is nothing majorly different about stoichiometry involving gases. We can broadly split it into 2 categories. We've done mass stoichiometry before. Now we're going to look at mass volume stoichiometry and volume stoichiometry. The good news is it's not any more difficult, and in some respects volume stoich especially is actually a little bit easier. So let's have a look at mass volume stoichiometry. In the past, we've asked you to calculate the mass of a product or reactant involved in a reaction by, for example, giving you, say, a mass of CH4, asking you to work out what mass of H2O will be produced at the end, for example. You've then taken that mass value for CH4, converted it into mole, used the mole ratio to work out how many mole of H2O we should end up with, and then backwards converted using molar mass to the mass of H2O. So what we can do when we've got gases involved is we can go one step further. We know that there is a set molar volume for certain conditions. All right, we've given you SLC and STP as conditions that we expect you to know. So we can compare and work out what volume of a gas will be produced in a particular reaction, because we can convert the mole that we have of a certain substance into the volume of that gas. So let's have a look at this question. Here we have the standard complete combustion of methane here. We're going to ask what volume of CO2 will be produced at SLC if we have 4.51 grams of CH4 reacting with excess oxygen. So follow exactly the same process as you would for any other stoichiometry calculation. Circle your unknowns, underline your known sets of data, and then set about your problem. Okay, so we have 4.51 grams of CH4 to start with. We still need to convert that into mole before we can go any further. So our amount of CH4 will be equal to our mass over our molar mass of CH4. Now our molar mass of CH4 will be 12.0 plus 4 times 1.0, so 16 grams per mole. So 4.51 grams divided by 16.zip gives us 0.282 mole. There's our amount of CH4. Now, we go through the mole ratio just like we always would. Okay, in this case, our ratio of CH4 to O2, sorry, to CO2, I should say, okay, is a 1-to-1 ratio. Because of that, our amount of CH4 will equal our amount of CO2. So we'll also have 0.282 mole of CO2 produced. Okay, this is where our last triangle comes in. Okay, so our triangle that has volume, molar volume, and amount. Okay, very similar to the mass, molar mass, and amount triangle. Okay, so now we know that our amount of CO2 is 0.282 mole. We know our molar volume at SLC is 24.5 liters per mole. Therefore, the volume of CO2 that we have is equal to the amount times the molar volume, so 0.282 multiplied by 24.5 litres, which will give us, rounded to 3 significant figures, 6.91 litres of CO2. Okay, so you can see the process here is essentially exactly the same as the standard mass stoichiometry you've done in the past, except instead of turning this amount in mole back to a mass, we're converting it to a volume instead. Try the example on page 13 in your book, and obviously gases assignment and textbook questions as well. Last but not least, but in some respects actually simpler, we have volume-volume stoichiometry. Niftily, because all gases share the same molar volume for a given temperature, all gas, no matter what it is, be it SO2, be it carbon dioxide, be it oxygen gas, be it methane, at SLC will all have a molar volume of 24.5 litres per mole. At STP, 22.4 litres per mole. It's the same for each and every gas. So, if we have information about the volume of one gas in a reaction, we can use that straightforward in a ratio to work out what the volume of another gas is. Okay, so obviously in the combustion of methane, we'll get H2O produced as a gas. You do have to be careful with this because obviously H2O will only exist as a gas in reactions that result in H2O being at over 100 degrees Celsius. I think in the combustion of methane, we can kind of assume that's going to be the case because realistically it will. So what we would do here is we would use the ratio of the mole ratio of CH4, compare it to the mole rate to H2O, and that ratio will allow us to work out what the volume is. Okay, so normally we would go through and we could go backwards and turn this 3.4 litres of CH4 into an amount using our new triangle here. Okay, we can go all the way back through. That 3.4 litres of CH4 will correspond to a particular amount at SLC, for example. Then we could convert across to H2O using the mole ratio, and then take that mole of H2O and convert that back to a volume. But we can only do that if we actually give you a set of conditions. So if, for example, we'd said at STP, okay, because then you have a molar volume you can use. But sometimes we may not actually give you those conditions. Importantly, with volume-volume stoichiometry, you don't actually need to know them, because whilst we don't give you a value for a molar volume at every single pressure and temperature that exists, if we've got this reaction happening, all of the products and reactants are going to be present in the same conditions. So we don't need to go through all of this conversion to be able to directly compare the volumes to each other. What we can do effectively is treat the mole ratio of CH4 to H2O as being equivalent to the volume ratio of CH4 and H2O. Okay, because they're both gases, they'll have the same molar volume, so the mole ratio is the same as the volume ratio. In this case, that is 1 to 2. We know we've got an excess of O2, so that we don't have to worry about that. So that means that the volume of H2O will be equal to 2 times the volume of CH4. In this case, 2 times 3.4 litres equals 6.8 litres. Nice and straightforward. I'll show you a slightly more complex example using limiting reagents in the next slide. Okay, so here we'll use the same equation again, but let's consider that we have a limiting reagent in this question. Okay, so we're going to give you two sets of data. We have 2.3 litres of CH4 and 4.1 litres of O2. Okay, ignore that coefficient there. So what we want to know is what volume of CO2 we're going to get produced in this particular reaction. To work that out, we need to know which of CH4 and O2 will be our limiting reagent. Okay. Now, I'm going to do this two ways to show you how it compares. Let's imagine for a moment that we've asked for this at standard temperature and pressure. What we would first do is we would take our 2.3 litres of CH4 and convert that back to an amount. Okay, so that will be volume over molar volume. In this case, 2.3 divided by 22.4, which gives us 0.103 mole. Okay. We also need now to convert our 4.1 litres of O2 back to an amount. So our amount of O2 will again be equal to volume over molar volume. So 4.1 litres divided by 22.4, which gives us 0.183 mole. We can then go through and compare the mole ratio. So our amount of CH4 to our amount of O2 is a 1:2 ratio. Ergo, to react all of that CH4, we would need twice the amount of oxygen. So that would be 2 times 0.103 mole. So we would need 0.206 mole of O2, okay, to react all of the CH4. Now obviously we know that in reality we have less than that, so that tells us immediately that O2 is the limiting reagent. We could then go through and do the mole ratio again to go our amount of O2 to our amount of CO2 is 2 to 1. So our amount of CO2 will be 1/2 the amount of O2. So that's 0.183 divided by 2, which is 0.0915 mole. I'll carry the extra sig fig for the moment. We want to know the volume. We know it's at STP, so we can then take our volume of O2 to be equal to amount times the molar volume, so 0.0915 times 22.4 gives us 2.05 litres. That's the long way to do it. Okay, that's going through and converting every volume back to a mole, running the mole ratio, working out the limiting reagent, then working out how much CO2 we'll have. So that should be CO2 down there. And then calculating using the molar volume what the volume will be. But because all of these values are gases, we can only do this when everything in the calculation is a gas. But because in this situation, everything that we're actually calculating is a gas, we can run this. Okay. What we can do is we can treat the volume ratio as being the same as the mole ratio. So we can look at the volume of CH4 compared to the volume of O2, just like the mole ratio, is a 1:2 comparison. So to react all of the CH4, we would require twice the volume of CH4, which in this case would be 2 times 2.3, So we would need 4.6 litres of O2. Obviously, we have less than that. We have 4.1 litres. So that means that O2 is our limiting reagent. Armed with that knowledge, we can then go to our next step where we compare the volume of O2 to the volume of CO2, okay, which is a 2-to-1 ratio. So therefore, the volume of CO2 must be equal to 1/2 the volume of O2. So in this case, that's half times 4.1, which gives us 2.05 litres. And there's our answer. It's effectively exactly the same process, but it's a shortcut because we don't have to go through extra steps of converting back to mole, running all the calculations, and then converting back to volume. All right? But I will stress, this only works if everything that you're calculating with is a gas. So if you have, for example, magnesium plus hydrochloric acid leading to magnesium chloride and H2, you aren't going to be able to run a volume-volume stoich because you only have the H2 gas being produced at the end. Everything else is either an aqueous or a solid species to start with. So you can only do this when gases are what you're calculating. Fundamentally, that's it. Everything else in the course came before last Wednesday. If you have any questions, email me over the weekend. Make sure you complete the gases assignment. Make sure you complete your text questions. And if you need, make sure you ask. Have a good weekend, girls, and good luck for the exam.